What's up, guys? This is Jahangir from MedPorium, and today we're going to be talking about Bronsted Lowry acids and bases. So let's actually dive into what that actually is, and let's start with the Bronsted Lowry acid. So the Bronsted Lowry acid, and I'll just copy this and just say that that's Bronsted Lowry acid. So Bronsted Lowry acids are classified as donating protons. So I'll just put donate, and let me get a new color, donate protons. But the protons are usually going to be hydrogen ions. Now, the reason why hydrogen ions, and we could just say H plus is a proton, is because hydrogen by itself has one electron and one proton. But since it has this plus charge, it only has one proton. And that's why we say that hydrogen ions are basically our protons, because in its essence, this isotope or this form of hydrogen is basically a proton. So Bronsted Lowry acids donate hydrogens, and that's why they're classified, or protons, and that's why they're classified as Bronsted Lowry acids. And if we look at Bronsted Lowry bases, this is pretty much the opposite. And you will see that when we talk more about acids and bases, that they're pretty much the opposite. They're pretty much opposites. So this would be a Bronsted Lowry base would accept protons. So now that we know the differences between Bronsted Lowry acids and bases, we need to talk about conjugate base and conjugate acid. So with this Bronsted Lowry acid, and I'll just copy paste this, the Bronsted Lowry acid will turn into a conjugate base. So conjugate, and let me just copy this, conjugate base. So on the reactant side, if you see a molecule that's donating protons or these hydrogens, which would be our Bronsted Lowry acid, then on the product side, you'd see a conjugate base. So what's an example of this? Well, we could look at something like hydrochloric acid. So hydrochloric acid, and that goes to just chlorine. So this hydrochloric acid is donating its electron, or donating its proton. It's losing this hydrogen over here, making it an acid, and this CO minus is our conjugate base. So our HCl, our hydrochloric acid, is our Bronsted Lowry acid. It's donating that proton to form this conjugate base of chlorine. Now, what about our Bronsted Lowry base? Well, that's going to have a conjugate acid. So if we do copy paste right here, so our Bronsted Lowry base will turn into a conjugate acid. So conjugate, and let me just copy this, acid. So what's an example of this? Well, we could look at something like NH3 or ammonia going into NH4 plus or ammonium. Now, as you can see, this is a Bronsted Lowry base because it is accepting a proton at the end. So this NH3 will accept a proton, and this ammonium is our conjugate acid. This NH3 is our conjugate base. So when you're trying to determine if it's an acid or base, always look at what happens at the end. What action happens, and whatever that action is, that's what that reactant pretty much is. So if that didn't really make sense, here's what I mean. So with this Bronsted Lowry acid, we can see we're going from HCl to Cl. So what action is happening? Well, we're losing a hydrogen. When we're losing a hydrogen, we're basically donating it, and that's why this is an acid. So this reactant over here would be our Bronsted Lowry acid. Same thing over here with that ammonia. When we go from NH3 to NH4 plus, we're gaining a hydrogen. That's the action. And what do we remember from gaining a hydrogen? Well, that's going to be a Bronsted Lowry base. And that's why our reactant is a Bronsted Lowry base. Now here's a way we can use Lewis structures to really understand how these acids and bases turn into conjugate acids and conjugate bases. So let's do something like HCl that we had in our example. And for the Lewis structure, we'd have something like this, since Cl has 7 valence electrons, so we want to fill that up. Then we add our water. So maybe something like this. And let me just move this to have a little bit more space. And those are our reactants. So we have HCl, hydrochloric acid, plus water, because this is in a solution. And this will turn into, and this is also in equilibria. So let me just put those right there. This is going to turn into hydronium, which is H3O plus. And we have that plus charge up top. And we have Cl, our chlorine, minus charge. And we fill in all those, fill in that octet. So here is our Lewis structure for that one example we were talking about with the Bronsted acid and conjugate base. The HCl going to plus water going to hydronium plus chlorine. So here's what really happens. So this hydrogen over here, since we know that this is a Bronsted Lowry acid, it's going from HCl to Cl, what happens is this hydrogen, once it is released from the chlorine, it will make a bond with this oxygen right here, that those 2 electrons, it'll make a bond, sort of similar to this bond over here, and this Cl, the bond between the hydrogen and Cl, these 2 electrons right here, because these represent 2 electrons, that's what makes that straight line the bond. Those 2 electrons will move to the chlorine. So let's just write this right here, just identify this. H plus bonds to oxygen, and 2 electrons move to Cl minus, and that's what makes Cl minus over here, because as you can see, those 2 electrons moved over here, and this hydrogen bonds to the oxygen to make hydronium. So this is the action that occurs looking at these Lewis structures and these transfer of electrons. So this hydrogen is donating, or excuse me, the hydrochloride is donating that hydrogen to the water, and that forms a bond that we can see over here. And those 2 electrons from that bond will move to the chlorine to form chlorine minus, or just this element form. And that's what it looks like from a Lewis structure standpoint. And these curved arrows over here that you might see in maybe your practice questions or anything like that show the transfer of electrons. Now that we know that, let's go through a practice problem real quick. So in this practice problem, we have H2SO4 and plus water. This is an equilibria, and this will turn into hydronium and HSO4 minus. And the question is, what is the acid, the base, the conjugate acid, and the conjugate base? So let's just write it over here. So I'm going to write what is our acid right here, then what is our base over here, and let's say right here conjugate, and I'll put base, conjugate base right here, since we know that if it's an acid, and I just put acid and base, but you already know it's Bronsted Lowry acid and base, because we're talking about Bronsted Lowry acid and bases in this video. So that's conjugate base right there. Then we're going to have conjugate acid right here. So now we got all that labeled. Pause the video and see if you can identify which one is the acid and the conjugate base, and which one is the base and conjugate acid. Alright, so let's actually move this stuff down here so we can do a little bit of work here. So Let's look at the sort of chemical formula. So we have H2SO4. So the first thing I want to look at is like my first reactant. So H2SO4. What happens to that? Well, we go from H2SO4 to HSO4 minus. So obviously we lost a hydrogen. And since we lost a hydrogen or a proton, obviously we have this minus sign right here. So we're losing a hydrogen. So I'll put loses hydrogen plus, and we know that if we lose a hydrogen, which is basically donating proton, then we know that H2SO4 is our acid. So if H2SO4 is our acid, then HSO4 minus is our conjugate base. So I'll just put HSO4 minus. That is our conjugate base. Now that we know that, let's look at water and hydronium. Well, water and hydronium, if we look at the hydrogens, there's more hydrogen on the hydronium. So we obviously gained a hydrogen, gained a proton. And because we gained a proton, we accepted it, and that means we are a base. So water is our Bronsted Lowry base, and obviously if water is our Bronsted Lowry base, then hydronium is our conjugate acid. So when you're trying to go through these problems, always the first step you need to do is look at your reactant side. And whatever that first molecule is, just pay attention to that one first and see what happens on the product side. And the reason why I knew how to follow that H2SO4 is because obviously we have this SO4 part, which is unique to that specific molecule. So on the product side, I just have to look, well, which part of the molecule has that SO4 and just compare them. So compare the reactants, compare the products. Then you want to see what action occurs. What difference happens between that H2SO4 and the HSO4 minus. And pay attention to the hydrogens because Bronsted Lowry acids and bases are defined by donating or accepting a hydrogen. So when you're looking at these Bronsted Lowry acids, always pay attention to the hydrogens. So I'll just even write that as a note. Pay attention to the H pluses, those hydrogens. You really need to pay attention to those. And when you see those differences, then you ask yourself, is there more hydrogen or less hydrogen on the product side? So what action occurs? Once you know that, then you can easily define which one is the acid and base, and whatever that acid is on the reactant side, well, the product is going to be the conjugate base, and whatever the base was on the reactant side, that's what's going to be the conjugate acid on the product side. So always remember, acid to conjugate base, base to conjugate acid. Once you got that, then you're pretty much unstoppable with these type of questions. Alright, so that pretty much wraps up our video on Bronsted Lowry acids, and it was a pretty quick video because knowing this really helps you build the foundation towards understanding how acids and bases react. Hopefully this video helped in any way, and as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.